Okay, off we go. So welcome back, everybody. Hope everybody had a good weekend. What we were talking about last time, of course, is Green's theorem. And the big idea of Green's theorem, well, okay, a point of view on Green's theorem is that these two integrals are going to give you the same value. Right, so now you can use this in either order. Typically what we find, it's most useful when you find yourself interested in computing a circulation, right? So that's a vector line integral. Very importantly, easily glossed over. It has to be a vector line integral around a closed curve, namely in particular a boundary, right? So let's not lose sight of that. It's got to be a boundary vector line integral. In other words, a circulation. It's nice to have a crisp single term to represent what that is. So circulation, and you can compute that circulation with a double integral of the curl of the vector field. Right? So pretty neat trick. And in fact, let's see here, last time we saw a couple of examples. We saw this example here where, there was a little bit of a twist. The curve that we were interested in was not a boundary. It's not oriented the correct way. The orientation matters. The word boundary means oriented according to a particular arbitrary but standard convention. Right? And so this is not a boundary. Okay, no big deal. All we had to do was just recognize that, but if I go the other way, and of course we have to insert a minus sign to account for the fact that we're going the other way, because orientations amount to a minus sign, then this is a boundary, and then Green's theorem, yada yada, it's all over from there. And then we saw another example where the curve we were given is kind of a weird curve. It sort of crosses over itself in a sense. And what we found is that you can break it up into two pieces, one of which is a boundary and one of which is exactly the opposite of a boundary. And so again, pay attention to the orientations. We turn it into a double integral and bam, answer. Okay, so that's what we were talking about last time. And let's see here, picking up from there. And let's see kind of an application of Green's theorem. This is a weird application. It kind of comes out of nowhere. So follow along with me, but you'll notice this right here is in fact just Green's theorem. That's all it is. We have a circulation on the left. We have a double integral of curl on the right. Now, of course, it's Green's theorem as applied to this very particular vector field. Why would I want to apply Green's theorem to that one particular vector field? What's that got to do with anything? How is this not just arbitrary silliness? And the answer is, this is a vector field whose curl is exactly 1. That's kind of neat, right? So if the curl is exactly 1, notice that double integral then on the right is just a double integral of 1. I'm adding up a bunch of little pieces of area. No surprise, that gives me then the area. So on the right-hand side, I get area. Now, what about the left-hand side? What does this turn into? And this is just a notational thing. I'll remind you what I have circled in red there is just rewriting that vector line integral on the left using coordinate line integral notation. So we talked about that at the end of chapter 5, end of 6.1, end of 6.1 I think it was. And it's just kind of a notational alternative. In most cases, it's bulky and inconvenient and counterintuitive. In most cases, I don't care for it. But this is one instance in which it's actually pretty handy. I mean, you're going to notice that this is a lot more compact of a notation than that is. So, every so often it ends up being kind of handy. And probably for this reason, you'll see this written like this most of the time. Okay. All right. So all together, now you see there's various sort of moving parts that make this line of algebra work out. But on the left, we have a circulation, and on the right, we have an area. right? And so this is a pretty neat theorem altogether. Let's put it all together here. Altogether, that integral around the boundary of some region D will compute the area of that same region D. Boundary line integral computes an area in this case. So, all right, why would this be a win? Area is something that, I mean, you've computed area a million times, high school geometry and stuff like that, not clear that we need to pull out big guns like vector line integrals to compute it. It turns out this is really helpful in a lot of circumstances. In particular, this integral can be really easy to compute sometimes. So here's an example. Now, this does have to be, I'll remind you, around a boundary, right? Boundary of the thing whose area you're interested in. So the following, it does not do that. The following is that integral computed over just a line segment. Not the same thing, and furthermore, a line segment cannot be a boundary by itself. It just can't do it, right? But look how easy it is to compute. It's bonkers easy to compute this specific line integral over a straight line segment because it's just the average value of x times the change in y. It's arithmetic, right? Simple. 4-function arithmetic, right? Really easy computation. And what's that got to do with boundaries? Well, sometimes the boundary is made up out of several line segments. So here, putting it all together, let's see all of this in action. Here is a pretty hard geometry problem, a nasty little geometry problem. And that is, let's try to figure out what is the area that is enclosed by this curve right there. What is that area? Well, yikes, right? I mean, you can break this up into various little pieces. I mean, I can kind of close that off, and then do like this, and that, and that, and that, and now I have 7 triangles. I can compute the area individually of each of those 7 triangles, and you're going to notice pretty quickly they're mostly not right triangles, which means each one of these is a hard geometry problem, right? So this is a little bit of scary of a computation. Okay, so what we're going to do is the above theorem. The above theorem says that if you want to compute, I wanted to change the color. If you want to compute this area, right, you can compute that area by just doing a boundary circulation, x dy. And how am I going to compute that boundary circulation? Well, this boundary circulation is the sum of a bunch of individual line segments. So you take that line segment right there, right? I equals 1. That's the first. I numbered them arbitrarily, but that's what I'm calling the first line segment around the boundary of this thing. Line segment integral x dy, I can compute with this very simple formula. I just have to look at what's the average value of x, what's the change in y. I think you can probably persuade yourself the average value of x is what's halfway in between 1 and 12, which would be about 6.5. Right? You can see further that the change in y, delta y, well, y started at 1 and went up to 6. Specifically, delta y then is positive because it increased, it went up. Right? So delta y could be negative. Right? So be heads up for that possibility. But anyway, x bar easy to compute, delta y easy to compute, the product easy to compute. Boom, we've just computed a vector line integral on one of those edges, and now keep going. And you just have to do this a total of 9 times, right, going around the edge. So, some arithmetic. It's a little bit of inconvenience, right? But it's way easier than your alternative. Alternative being to deal with those non-right triangles and trying to compute their areas. This is tricky business. Right? So very nice solution to what would have been a nightmare of a problem. Okay, so I'm going to encourage y'all to check the rest of this arithmetic. Just make sure you see the process. In particular, as we've discussed, this line integral is computed by that arithmetic right there, and then that one by this arithmetic right here, and then that one by this arithmetic right here. Hey, notice on that third one, delta y is negative because y decreased going in the correct direction along that line segment. So you got to pay attention to that. Be careful with that. Okay. All right. How we doing? Everybody following along? Okay. Kind of a neat trick. Useful sometimes. Okay. All right. So next thing we're going to talk about is flux again. Y'all have seen flux previously, right? Back in chapter 3, we talked about how if you have a fluid flowing through a surface. So we were imagining, obviously, a three-dimensional fluid, and then I have a surface. Maybe the fluid is air, and the surface maybe is a screen. The air is, let's say, flowing through the screen. Or again, maybe we have water, and we're talking about water flowing through a net, something like that. Right? And we came up with a formula not terribly different from what you see here. Now, the difference is, here we're considering flux through a curve. We have a two-dimensional scenario, a two-dimensional fluid represented by a two-dimensional vector field, right? And same basic idea of a question. As the fluid flows like this, given a line segment like that, I can talk about, okay, well, how much, in whatever appropriate units you'd like, how much of this fluid is flowing across that line segment in any given period of time, right? Per unit time. What's the flow rate, quantity of fluid per unit time flowing across that curve? And I think this is a fantastic exercise. I want to encourage y'all to compute this. The way you're going to do this is you're going to flip back in the notes to chapter 3. You're going to see how we did the analogous computation in 3 dimensions, where we were interested in volume of fluid per unit time. Here, you're going to compute area of fluid per unit time. Right? And go through a totally analogous computation. In fact, it's quite a bit easier in this case because you don't get a 3-dimensional parallelepiped of fluid. You get a 2-dimensional parallelogram. Much easier to draw, right? Much easier to kind of deal with the geometry of it. You just get a parallelogram's worth of fluid in any given period of time and compute the area of the parallelogram, divide by delta t. Everything's going to work out very nicely. Okay, so like I say, lovely exercise. I hope you'll give that a crack. And here's the answer. And you'll notice how similar this is to the formula we got in chapter 3. Okay. All right, so what we're going to entertain now is a related question. And I'm temporarily going to scratch off some stuff that I don't want you to pay attention to just yet. Don't look at this just yet. We'll get to it in a minute. So what we want to do at the start here is entertain the question of a boundary flux. Not just a flux through some curve, but a curve that is a boundary. So in particular, we've got some region here, and the boundary is some curve that, I'm only showing you just a part of. I mean, you could imagine that this kind of wrapped back around, something like that. But let's just think about one little part of it. And how would I compute the total boundary flux? I hope it comes as no surprise, but as we do so often in this course, we're going to take this and we're going to chop it up into little pieces. And I'm going to say that the grand total boundary flux is the sum of the boundary fluxes over those individual little pieces. On any individual little piece, and let's see here, Ooh, can I, yeah, okay, got it. Wow, that was nice. Oh, okay, got it again. Okay, so on any individual little piece, if I look at, let's say, this little piece right here, that little piece of fluid, or excuse me, that little piece of curve, how much fluid is going through that little piece of curve? The fluid going through that little piece of curve, which is approximately a line segment, I can compute with the formula on the previous page. Right? It's F dot N times the length of that little piece of curve, and of course that's a little piece of curve, we'll call that length ds, as we always have. Okay, how are we doing on that part? Everybody on board? Notice that's just a sort of an immediate application of this right here, F dot N times the length of the piece of curve. That's what we have here. Okay. All right, and at this point, we have a problem. A little bit dead in the water here. How do I compute this integral? Great. We've never seen this integral before. We don't have any handy formulas. How do we do pullbacks of an integral like this? We know how to do f dot t ds, because t ds is dr, and we just got all sorts of formulas for that. This is f dot n ds. It's totally different. How are we going to get our hands on that? And one thing you can do, and this we don't really want to have to do this, but hypothetically you could parameterize and you could write down some explicit formulas in terms of the parameterization and get down into the the geometry of it all. All else being equal, it's preferable not to have to do that. So here's why I have the rest of this stuff on here. This stuff that I scratched out previously allows us to get our hands on the idea of what is f dot n. This dot product right there. We've got our vector field f, p comma q. We've got our normal vector, right? Our normal vector n. Important detail about the normal vector. We have a convention when you talk about a normal vector describing a part of a boundary. There is another convention. Boundary in this case means outward, away from the region whose boundary you're talking about. Arbitrary convention, again, totally arbitrary. Math could have been built up with the opposite convention. There'd be some differences in how things work out, but basically everything would work out. But again, that's not the choice that got made, right? This is the convention, this is the standard, and this is therefore non-optional. Okay, so that's just the convention. So how do we compute this dot product? And here's the clever argument. I wish I thought of this myself. The big idea here, if you just rotate both of those vectors 90 degrees counterclockwise, quick appeal, you rotate both of the vectors, right? Here's the two vectors. If you rotate both of them, the angle between them doesn't change. The magnitudes don't change. Dot product is computed entirely in terms of magnitude and angle between, none of which change. So in particular then, when we rotate around, the dot product doesn't change. And so this dot product that we have, this purple dot product, f dot n, that I have here that I'm not happy about, because I don't know how to compute that integral, that's exactly the same as this dot product. What you get when you just rotate those two vectors. And quick geometric appeal, if you have an outward oriented normal and you rotate 90 degrees, you get the unit tangent vector, namely the one that puts the region on the left. That's purely a geometric appeal. You see there in the picture, if you're going outward from the region and you rotate counterclockwise, the region's on your left. Everybody see that? Okay. So beautifully, that purple dot product is exactly the same as this
Now, dark blue dot product, and I like that dark blue dot product for the simple reason that I'm familiar with it previously. Here it is. I've got TDS. Oh, fantastic. We remember TDS. That's just DR. We have here just a good old-fashioned, regular old vector line integral. Around a boundary, no less. So that's a circulation. And given that we have a circulation, we can invoke Green's theorem. This is the big gun that does most of the heavy lifting in this calculation that we're in the process of doing. We had to kind of finesse things a little bit to rewrite our flux integral as a vector line integral. But once I got it in that form, Green's theorem, and now it's just a matter of kind of rewriting a few things. And here we go, rewriting. Having written Green's theorem like so, apparently I'm going to need to compute curl. How do I compute curl? Now, be careful here. I'm not interested in curl of F, right? Notice we did this 90-degree rotation. Forget about F. No longer F. We're interested in the curl of F perp, the result. The vector field that results from rotating the field vectors 90 degrees counterclockwise. And that's not P comma Q, that's minus Q comma P. Now again, that's a linear algebra thing. Make sure that you're comfortable with that. How do you rotate a vector 90 degrees counterclockwise? It's a linear transformation represented by a matrix. The columns are the images of the standard basis vectors. Make sure you can play that game. It's a really important process. We're going to use it a lot in this course. You're going to use it a lot outside of this course as well. So the rotation of PQ is minus Q comma P. And now to compute the curl, easy mistake to make. A lot of people just kind of memorize alphabetically, dq dx minus dp dy. That's what it is. And it's not really. Let me go back to, Yeah, here we go. Our formula for curl right here, circulation density, this formula, it's the x partial of the second field coordinate minus the y partial of the first field coordinate. Right? Remember, it's not about the alphabet. It's about which variable is in which place. So, second coordinate with respect to x minus first coordinate with respect to y. And so applying that here, notice we have second coordinate with respect to x minus first coordinate with respect to y. Is that all right? Everybody's okay? All right, and then it's all over but the shouting. Obviously, these minus signs cancel, so we get rid of them. This then simplifies to this formula, which we then recognize, oh my gosh, that's this formula called divergence that we wrote down in chapter 3. And poof, it just appears, right, seemingly out of nowhere. And this is our first glimpse at what we call the divergence theorem. This is called the two-dimensional divergence theorem, that if you have a outward-oriented boundary flux to compute, boundary, again, it's got to be a boundary flux, very important that it be a boundary. You want to compute an outward-oriented boundary flux, boom, double integral of divergence. We'll do it for you. What do you think? Everybody all right? Let's see this in action. By the way, I'll come back and talk about this in just a moment. It's just a notation thing. But I want to get a win in the win column first. So here's the question that we face. We're going to look at the unit circle, and it says compute the outward oriented boundary flux of this vector field. And, again, if you really wanted to, I suppose you could write this down and parameterize, and then you'd have to get some dirt under your fingernails to figure out the formula for the normal vector in terms of the tangent vector. But you could write every part of this in terms of a parameterization and, deal with it like that. It's doable, but this is so much better to do it as follows. And that is to just recognize, an outward-oriented boundary flux, double integral of divergence. Let's let that do the heavy lifting for us, right? Realizing it's a double integral of divergence, I just have to compute the divergence, and for this vector field, the divergence works out really nicely. It's just -3. So all the ugliness in that formula for that vector field, we've got an exponential, we've got a cosecant, right? One of the weird trig functions. It just disappears. Because now, to be fair, this is a highly manufactured example, right? I arranged it that this would work out awesome because I'm trying to make the sales pitch of how cool this theorem is. Won't always necessarily be that awesome, but you got to give it to me. In this case, that worked out really awesome. And this, what would have otherwise been difficult flux computation, in which I would have had to deal with exponentials and weird trig functions and parameterizations and a lot of details and how do I write down the formula for the normal vector and a lot of stuff, turns into, let's see here, how do I integrate a constant over a disk, which is a snap. Anybody buy it? Okay. All right. Lovely calculation. Okay, now let's go back up here and deal with this notational thing. This is just a notational thing. As it turns out, there is an alternative notation for this flux integral. It's this. You'll notice it uses the wedge. And again, reminder, we talked about the wedge back in chapter 1, I think it was. It's kind of a two-dimensional... it's kind of like determinant in certain ways, and it's kind of like cross product in other ways, and it's just a formula, and it's just a matter of sort of writing these things down. But one of the things you're going to notice, and this is an easy exercise, again, I think this is a healthy exercise. I hope everyone will do this. Give it a crack. That a dot product is a wedge product where you just rotate the second vector counterclockwise by 90 degrees. So just as a reminder, this perp there is the same as that perp right there, 90-degree rotation counterclockwise. So now this is an easy calculation. Make sure you can do that. And then capitalizing on that, you see, we have this f dot n. We have a dot product. And using this theorem, I'm going to rewrite that dot product as a wedge where I just have to, I just have to remember, don't forget to rotate that second vector 90 degrees counterclockwise. And of course, when you rotate the normal vector, you get the tangent vector, as we discussed earlier. No big deal. And then, of course, you recognize TDS is DR, and so boom. So kind of a nice notation. It's a notational alternative. You don't have to use it, but you do have to be aware of it. Someone else in your circle may use it, might show up on an exam, for example. Again, this is a notation that you are responsible for. So this might be written as that. Okay. All right. Moving along. Here's a different point of view. I think this is lovely. This is actually, I prefer this point of view I'm about to show you. On the previous page, we got our hands on the idea of boundary flux by finding a way to relate it to Green's theorem. The Green's theorem did the heavy lifting for us. What we're going to do here is realize we don't need Green's theorem. Green's theorem came from noticing that circulations are an accumulating quantity. And there's a bunch of details that you have to follow through, which is, fine. The big point to realize here is that boundary flux, you don't have to relate it to circulation. Boundary flux on its own is also an accumulating quantity. And don't forget, when you have an accumulating quantity, right? And this flashes back to the start of 6.2, I guess it is. Whenever you have an accumulating quantity, you can think of it as being distributed over the area. It behaves like physical stuff. It has an associated density, which you can integrate to get an integral theorem, right? All you need is to have an accumulating quantity, any accumulating quantity, and boom, you've got yourself an integral theorem. So, that's what I'm going to observe here. Boundary flux is an accumulating quantity. Actually, I'll leave that checked. So if I look at this left piece, and here's what outward-oriented boundary flux looks like for the left piece. And if I look at the right piece, and here's what outward-oriented boundary flux looks like for the right piece, you can see again what it comes down to is, what about this shared edge in the middle that, it's part of the green boundary, it's part of the blue boundary, but it's not part of the whole boundary at all. It's not part of the boundary of the whole. It feels like this is the problem, in other words. But again, we get the same win that what we're talking about is an integral over this red edge twice with opposite orientations, and so they cancel. Right? The left flux through that curve is sort of obviously the exact negative of the right flux through that curve. Same calculations with a minus sign. Okay. So again, the discrepancy disappears, and that means that we have accumulation, and so boundary flux accumulates like so. And again, once you have an accumulating quantity, you write down the density, blah, 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 boom, theorem, and that is how you get the two-dimensional divergence theorem. So let me just remind you, it's the same density argument and accumulation argument that we made for mass. Mass is an accumulating quantity. We saw this a little scarier, abstract, uncomfortable idea that circulation is an accumulating quantity, and now we've just observed that boundary flux is an accumulating quantity. And correspondingly then, we can talk about the associated densities, and in the same way that we get mass density as the integrand there, and circulation density as the integrand there. A little bit of a weird way to think about it, but that's exactly what it is. Ultimately, that's where your intuition's going to be. I can't emphasize this enough. If you want to have some intuitive sense, what is this thing called curl? How should I think about curl? That's it. Circulation density. Circulation around the boundary per unit area on the inside. And then likewise, as it turns out, divergence is flux density. And again, fabulous intuition, really fabulous intuition. If you want to have a good intuitive instinct for, why do we care about divergence? It's because it tells you how much outward-oriented boundary flux there is per unit area of what's on the inside. All right, how we doing? Pausing again. All right. By the way, for your consideration, I will confess that this term here, circulation density, when I was your age, taking various math and physics classes, a lot of physics classes, physics just had heftier requirements when I was an undergrad. So this term circulation density, I don't remember actually hearing that very much, if at all. It's not a very common term, but again, I love this term because it is so descriptive. It is literally telling you how you should think about what curl is. So great term, not in anywhere near common enough usage for my preferences. But this one, flux density, extremely common. I heard it all the time. Flux density, oh, if I can get this to magnify. Come on, there we go. Flux density I heard more often than I heard the term divergence, which is the actual name of this operator is divergence. But in my physics classes, I heard the term flux density even more often than the term divergence. So very common use, right? That which I take as recognition of what a useful idea it is to think about these operators in terms of as being densities, and densities of what sort of accumulating quantity. Okay, so for your consideration. All right, let's see here. Now I got to get the thing settled again. Okay, there we go. Okay, moving along. I want to remind y'all of the fundamental theorem of calculus, which I recognize a little silly. Y'all know the fundamental theorem of calculus, right? It's integral, right? F of b minus f of a, all that business. I hope everybody remembers that theorem. Huge theorem. You've used it a million times. You've thought of it previously as a way to compute integrals, and I want to give you a different angle on this. This is a fabulous point of view, by the way. My purposes here are not to actually change how you think about the fundamental theorem. My purpose here is to give you an alternative way to think about the fundamental theorem that will support these points of view that I'm giving you about Green's theorem and the two-dimensional divergence theorem and various more theorems that we're going to see on down the road. And in particular, the fundamental theorem of calculus itself is the result of an accumulation argument where you integrate a density. And again, this is a very rare point of view, almost never pushed, but I think this is fabulous. All we have to do is recognize that this expression, aka change, accumulates. The whole is the sum of the parts. Now, it's just an appeal, right? I think we could write down some algebra, I suppose, if you wanted to, but I think this is a pretty relatable idea. If you just think about, okay, well, let's see here. My bank account has this much money in it, and then if you check back in a month, and it has changed, right, by this amount, now you have this much money, right, but the change was this amount, and then from there, in the next month, it changes again, let's say by this amount, thus putting you here. The overall total change is the sum of those individual changes. Well, of course it is. Right? If your net worth increases by $1,000, wouldn't that be nice? $1,000 in 1 month and then $2,000 in the second month, not a deep observation to have noticed that your total change over the 2 months was sum, 1,000 plus 2,000, right? It's perfectly obvious if you think about it. So we have an accumulating quantity, and when you have an accumulating quantity, you can think of it as a stuff, and you can talk about the density and blah, blah, blah. And in fact, this theorem, the fundamental theorem, right, f of b minus f of a, colors. AKA change, being computed with an integral is just a recognition that change has an associated density. And it's a little bit of a weird way to think about the derivative, but the derivative, you can think of it as being a density. Now, this is another strange point of view, and I fully recognize, weird. Right? Let's talk about what y'all have seen previously. How have you previously thought about the derivative? Slope of the tangent line. Very common point of view. Nothing wrong with that. I'm all for it. relates to velocity in some circumstances. If you're talking about position, if your function represents position, then the derivative represents velocity. Right, standard, yawn. Now I'm going to push that you think of it as not as a slope, not as a velocity, but as a density. And again, counterintuitive, but let's draw a picture. I claim ultimately this should be no surprise. Change per unit size. Now the way y'all typically thought about the derivative, probably, is rise over the run. Maybe you think about it. The rise represents how much did the value of the function change. Right? And in particular, how much did it change over a little sub-interval down here based on its size? I mean, slope, I know, a weird point of view, I grant, right? But slope is, in fact, really telling you, don't think of it as rise over run, think of it as change, how much the value of the function changes, not per unit delta x, but per unit size of the corresponding piece of the domain. Change per unit size, aka change density. Okay. Weird take. Why do I like to push this point of view? So I want to flash back again. Let's see here. Now I'm on the wrong page. Yeah, let's go back to here. When we were building up this idea of accumulating quantities, and ultimately I was kind of laying the groundwork for writing down Green's theorem. And I made this, I'm going to confess, a little bit of a unsatisfying point of view of asking you to view an accumulating quantity as being distributed over the interior, right? And in particular, when you think about circulation in the context of Green's theorem, let's see, circulation in the context of Green's theorem, a little bit hard to imagine thinking of something that I compute literally on the boundary as being distributed over the interior. It's a big ask. It's weird. How could something that is explicitly computed on the boundary be thought of as distributed over the interior? And that's the first real big win that I think happens here when we think about the fundamental theorem of calculus from this point of view. Notice that's exactly the point of view we're taking here, and it's not a weird ask at all. If I were to tell you that change, so, f of b minus f of a, right? This is how you measure change, right? You look at f of a, you look at f of b, and change is this right here. Let me get rid of the distraction. Change says how much is f of b minus f of a. That's what change is. Notice again, it's computed on the boundary. Now I ask what I think is very intuitively reasonable. Okay, yeah, but where did that change happen? Here, right? You can see in the graph, you can see that that's where the function's changing. I can even see how much it's changing where. Of course the change happened there. Right? When I was 5 years old, I was this tall. Right? Now I'm this tall. That's a change in height. When did that change happen? Well, as I grew up, of course. Right? Not a weird point of view at all. Nothing even slightly weird about the idea here of something computed on the boundary actually being something that happens over the interior. Perfectly yawn, routine, nothing weird at all. That's exactly what I'm asking you to digest here. That something computed on the boundary, namely boundary circulation, can and should be thought of as actually happening in the interior.
Right, so I think that's a lovely feature. Okay, good enough. A lovely feature of this, thinking of the fundamental theorem of calculus like this is that I hope will make it a little easier to digest this idea of accumulating quantities happening on the interior. In this case, it's obvious. Okay. The second thing I want to point out is that another sort of really nice intuition that we get here is the idea that this integrand, this operator, this density is telling you how much specifically of the accumulating quantity in question is happening near a given point. So you can see where the derivative is large, right, where it's a steeper graph. Yeah, there's more change happening there. Well, of course it is. You can look at how much it's changing. It's changing a lot at that point in the curve. Where this density is lower, in fact, it looks to be about 0 there. Where that density is lower, there's no change happening there, right? So the operator itself tells you where the stuff is in the interior, right? Now again, we have to use our imaginations. This idea of the accumulating quantity is actually being distributed over the interior. But from that point of view, yeah, clearly there's more in the middle and there's less at the start and there's less at the end. And that's all we're going to do with, and by the way, this example here just quantifies that. No big deal. But if you want to know, between these 2 points, here and here, where's the change happening more? Well, no big deal. Look at the derivative. Right? You look at the derivative. Here's the values of the derivative. The derivative is bigger at 2. There's more change happening at 2 than there is happening at 1. Again, to look at the picture, it's steeper there. Yeah, greater slope. More change because there's more change density. And we can draw analogous pictures thinking about, for example, circulation. So, for example, let's look at the circulation happening on this. Oh, whoops. Let's look at the circulation happening on this curve. Now here we have a closed curve, like so. There's a total amount of circulation, whatever that is. I claim that that's happening in the interior somewhere. Well, where? And how much where? And so I claim you can compute Green's operator, and if you compute Green's operator, what you will find is that Green's operator is positive in this region, and it's 0 in that region, and it's 0 in that region, which, by the way, is something that you can even see coming, because if I draw like a little square right there, and let's just compute literally the circulation on that little square. If I can get this thing to, what did I just do? Oh, okay, it was just slept for a second there. If I compute the circulation on this square, notice on this edge, the field is going the same direction as the curve. I will get a positive contribution to the line integral there. Notice on this edge, oriented correctly, I'm going to get a negative contribution to the line integral. We are, in fact, the fluid is going opposite the direction of the curve. So negative contribution to the line integral there. And by the way, 0 at all the other points, because, for example, along in here, the curve is going that way and the fluid is going that way, and there your dot product's just straight up 0. So there's no circulation on that part of the edge. So grand total, you're going to get a large positive contribution and a smaller negative contribution, which adds up to positive. So again, you're going to get on that on that interior, you're going to get Green's operator positive. That's telling you that's where the circulation's coming from. You may detect the circulation. Oh gosh.
You may detect the circulation by doing a computation on the boundary, but it's not happening on the boundary. It's coming from, ultimately, the interior. And y'all can make an analogous computation thinking about flux, right? I think this is a nice exercise. You might compute outward-oriented boundary flux. You might compute that on the boundary, but where is it coming from? Think about a little square there. Think about a little square there. Think about a little square here. And what you're going to find is that it's coming from this gray area. In that gray area there, you're going to find that the outward flux on what you might call the right edge of the square is large positive, and then there's inward on the left edge, but it's smaller. You're going to get positive flux, and therefore positive flux per unit area, therefore positive divergence in that gray area. And you're going to get 0 on the left, you're going to get 0 on the right. Totally analogous to the calculation we just did. So, in the same way that derivative tells you where change is happening, likewise, Green's operator tells you where specifically and in what density circulation is happening, and divergence tells you specifically where and in what density flux is happening in the interior. This is just a explicit computation that does exactly this. If you want to know where the flux is coming from, if you want to know where the circulation is coming from, look at circulation density. If you want to know where flux is coming from, look at flux density. And plug and chug, answers fall out. Okay, I'm out of time. We'll draw the line right here. See y'all later. Have a good rest of your Monday. See you on Wednesday. Oh, and by the way, my email, of course, is still down. I will absolutely send out an announcement as soon as my email resumes. Until then, communicate with me through my Gmail that I've already sent you emails from. Okay, see you later.